I will explain the problem of finding the sum of remainders when integers from 1 to n are divided by given number m. We start by creating a set A that contains all integers from 1 to n. For each number in set A, we calculate the remainder when it's divided by m. These remainders are stored sequentially in a new set B. Once all remainders are found, the elements in B are summed to find the total T. For example, if n equals 10 and m equals 5, the remainders are 0, 4, 3, 2, 1, 0, 4, 3, 2, 1, and their sum is 20. This process shows how algebraic manipulation can organize and solve systematic problems efficiently.
Let's talk about how to calculate pairwise sums. The goal is to find sum of every possible pair of numbers in a list. For example, consider 1, 2, 3. We will add each pair. 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 3 is 5. This gives us results 3, 4, 5. For a list of n numbers, there are n minus 1 divided by 2 pairs. This method is useful in data analysis when comparing all combinations. To summarize, just list all pairs, add them, and record the sums.
Let's go through how we solve this step by step. First, understand the input. For each test case, you're given two numbers, k, the maximum base, and n, the exponent. The goal is to find the sum of last two digits of I to the power n for all numbers I from 1 to k. Next, we used a shortcut called modular arithmetic to calculate powers efficiently. Instead of working with huge numbers, we start with the result of 1 and update the base I mod 100, and then while n is greater than 0, if n is odd, we multiply the result by the base and take mod 100. Then half n using integer division and square the base, again taking mod 100. We do this for each I, adding the result of I to the power n mod 100 to a total sum. After each addition, we take mod 100 to keep the sum within two digits. Finally, once all numbers are processed, print the total sum as two-digit number. For example, if the sum is 5, it is written as 05. This approach makes the calculation first and works fast and works even for very large numbers.
I solved this step by step. First, I created a sequence of numbers using the formula given, starting with 0 and the number 0. Each new number in the sequence was calculated based on the two previous ones, using the modulus m to keep the values manageable. Then I grouped these numbers into pairs to form vectors like A2, A3, and A4, A5, and so on. Using these vectors, I calculated their scalar products, which basically means multiplying and adding their parts, then taking the result modulo m. Finally, I looked at all the scalar products to see how many unique results there were. In this case, the answer was simple, just 2 unique results, and that's how I did it.
So let's take a look at the problem number 5, summing kn series. Here, the n term, Tn, we define it as n to the power kn, where n is the number of terms of the sequence and k is the power of each term. And Sn is the summation of all the terms from term number 1 to n term that we define. In here, we use modular arithmetic to keep the numbers in a more manageable region. So let's take a look at an example where n equals 5 and k equals 3. So in here, let's calculate each term from term number 1 to term number 5, and let's take the addition of all those terms, all the 5 terms, where the final solution is 225. So when we express in our final solution, we express it as 225 modulo 10 to the power 9 plus 7. So again, the final result will be 225. The main objective of using modular arithmetic is to get a final solution which is more compact and more accurate for even for large inputs.
Let me take you through the steps to solve the Fermi series problem. It involves two types of queries, comparing series and modular calculations. The first query involves two series, S1p and S2p. S1p is the sum of positive coefficients, and S2p is the sum of absolute values of negative coefficients, both calculated using modulus of 10 to the power 9 plus 7. By comparing these two series over a range, we count how many times S1 is greater than, less than, or equal to S2. The second query involves calculating terms of the sequence Gn using parameters Pu and V. After calculating Gn, we simplify it with modular arithmetic Gn mod V. These steps efficiently solve the problem, making complex calculations manageable.
Imagine you have a sequence of numbers arranged in a circle. Each number has two neighbors, one to the left and one to the right. The goal is to update each number based on the values of its two neighbors, repeating this process for several rounds. The following data are given. N, M. Each element a base to I represents the initial value of the ith position in the sequence. The game rules are as follows. First one, in the kth round, the ith element is updated by adding the value of its neighbors. An example is given below, where a base to I minus 1 is the left neighbor, a base to I plus 1 is the right neighbor. Second one, repeat the update for m rounds, rotating clockwise through the sequence. So output is as follows. This circular updating process continues until all numbers have been updated for the given number of rounds, and the final values are outputted.
The goal is to count the number of ways to distribute a total number n into k parts, where each part can be 0 or more. For example, if we want to divide 5 into 3 parts, we need to find all possible combinations where the parts add up to 5. This problem is solved using a method called combinations with repetition. It calculates how many ways we can distribute the total among the parts, considering that the order of the parts doesn't matter. For the example of dividing 5 into 3 parts, there are 21 ways to do it. To solve problems like this in general, you identify the total number of distribute and the number of parts, then apply the formula for combinations with repetition to calculate the result.
Today, I will explain the XOR KPR sum problem. We are giving an array of numbers and sum queries. Each query asks us to calculate something called KPR sum using three numbers, K, P, and R. The formula looks like this. Here, O plus means XOR, which is bitwise operation. Let's see how we need to solve a query. For each query, take all parts of numbers in the array from position P to R. Find the XOR each pair of numbers. XOR this results with K. Add up all these values. For an example, for the array A, 1, 2, 3, query K is equals to 1, P equals to 1, R is equals to 3. We calculate the pairs 1, 2, 1, 3, 2, 3. The result is 5. Query 2, K equals to 2, P equals to 1, R equals to 3. Do the same steps and the result is 4. So the answers are 5 and 4.
The series in question is sigma n equals 1 to infinity 1 by n into n plus 1. Each term in the series is given by 1 by n into n plus 1. To simplify each term, we decompose it into partial fractions. The decomposition shows that each term in the series can be written as the difference of two simpler fractions. Now we can express the series as n equals 1 to infinity n by 1 by n minus 1 by n plus 1. When we write out the first few terms, we see the pattern of how these fractions work. Observe that each positive term, 1 by n, cancels with the negative term minus 1 by n of the subsequent of fraction. This is known as a telescoping series. After cancellation, we are left with the only terms that do not cancel out are the first positive term and the last negative term. To find the sum of the series as n approaches infinity, we evaluate n limit infinity 1 minus n by n plus 1. As n become very large, 1 by n plus 1 approach 0. Therefore, the sum of the infinity series is 1.